Example 3.2. A. In example 3.1, the electron drift speed is estimated to be only a few millimeter per second for currents in the range of a few amperes. How then is current established almost the instant a circuit is closed? Because as soon as we close the circuit, the electric field is established in the conductor instantaneously. The speed of the electric field of propagation, that is equal to speed of light, and therefore instantly the local electrons are drifted under the effect of it, and the current is constituted. Clear? D. Each, sorry, the electron drift arises due to the force experienced by electrons in the electric field inside the conductor. But force should cause acceleration. Why then do the electron acquires a steady average drift speed? Because when free electrons experience the force and are accelerated, then during their accelerated motion it collide with another electron as well as ions, and their velocity, or we can say speed, becomes instantaneously zero, and then after again in another direction it is accelerated, and again when the collision takes place its speed becomes zero. So resultantly it moves in the opposite direction of the electric field. So we say here the average drift speed is acquired by electrons. Clear? See, if the electron drift speed is so small and the electrons charge is small, how can we still obtain large amount of current in a conductor? We get large amount of conductor in the conductor, large amount of current in the conductor, because the number of electrons, that is tremendous large one, or in other words we can say the number density of electrons in the conductor, that is tremendous large one. D. When electrons drift in a metal from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? No. If any electron suffer the head-on collision with ion, then it rebounds. So not necessarily all the electrons are moving in the same direction. E. Are the paths of electrons straight line between the successive collision with the positive ions of the metal in the absence of electric field? And 2. Presence of electric field. Yes, in the absence of electric field, the path will be a straight line. But in the presence of electric field, electrons experience the force. And when the force is acting on the particle, the path that will be curved one. In general, that type of path is followed by the particle. Clear? Now mobility of the particle, that is nothing but the drift velocity acquired by the particle or the charge carrier per unit electric field applied. That is the mobility, right? And the conduction process of the substance, or we can say of the conductor, that depends on the mobility of charge particle or charge carrier. So we can write mobility mu, that is equal to drift speed Vd upon electric field E. So this one is the drift speed acquired by the charge carrier or charge particle per unit electric field. Now, unit of drift speed, that is meter per second. For electric field, it is Newton per coulomb. So resultantly, we can write meter coulomb upon Newton into second. That is the unit of mobility. Or suppose we take the unit of electric field, that is volt per meter, then meter per second upon volt per meter. So that will give you meter square per volt second. Clear to all of you up to this one? Now, in this equation of mobility, substitute the value of Vd. So we can write 1 upon E into E upon m into tau. This equation of Vd that we derived in the previous theory. So E cancelled, and resultantly we can write the mobility mu, that is equal to E tau upon m. This is the mobility. Clear? Now limitations of Ohm's law. See, we already discussed this thing when we discussed Ohm's law. We mentioned this thing. Ohm's law is not the universal law. It is an experimental observation. And under certain fixed positions or situations, the Ohm's law is obeyed. Okay. See, Ohm's law suggests this thing. There is the linear relationship between voltage and current for the substance or conductor, we can say. Okay. Now see, suppose we think about the metals, which are very good or pure conductors. So for metals, when we plot the graph of voltage versus current, then as per Ohm's law, it should be a straight line. No doubt, up to certain temperature, the graph is a straight line. But if the temperature increases, then at higher temperature, the linear relationship between voltage and current, that will not be obtained. So this is one limitation. Okay. Then in certain conductors, means substances which give you conduction process, the VI relationship, that depends on the sign of voltage V. Understand this thing like this. See, suppose this is the conductor. હવે અત્યારે એવું વિચારો temporarily, this conductor is a metallic rod, copper rod. Now here across these two terminals, we connect a battery. And suppose positive terminal of the battery is here, negative terminal of the battery is here. Okay. Now, if we switch on the circuit from positive to negative, the current will flow like this. Okay. Now, if we change the voltage 1, 2, 3, 4, then in this particular direction, the current will also increase. Clear? Now, suppose in the same experiment, we change the terminals of the battery. એટલે આ બાજુએ આપણે પોઝિટિવ ટર્મિનલ બેટરીનો કનેક્ટ કરીએ અને આ બાજુએ નેગેટિવ ટર્મિનલ. Okay. Again, if we change the voltage 1, 2, 3, 4 like that, then the same amount of current will flow, but now in opposite direction. And the shape of the graph, that will be the same one. Yeah? એટલે 1 વોલ્ટે આ ડાયરેક્શનમાં જે કરંટ જતો હતો એ સેમ ટુ સેમ કરંટ 1 વોલ્ટે આ ડાયરેક્શનમાં જશે. ખાલી કરંટની ડાયરેક્શન ચેન્જ થશે, બાકી રિલેશનશિપ એઝ ઇટ ઇઝ થશે. બટ સપોઝ વી થિંક અબાઉટ ડાયોડ્સ. આપણે એના વિશે 14 ચેપ્ટરમાં લાસ્ટમાં ભણીશું. Diodes are semiconductors. Okay, so in that VI relationship depends on sign of V, means the polarity of the terminals. હવે જો માનો કે તમે પોઝિટિવ પોટેન્શિયલ એપ્લાય કરેલો હોય, and if you increase the voltage, current also increases but non-linearly. જો curved graph આવે. But if negative potential is applied and if the voltage is increased, initially very slowly current increases, and then after certain value of the voltage, all of sudden current increases. So here we can say this thing, Ohm's law is not obeyed. Clear to all of you? Then for certain substances, VI relationship is not unique one. See here, one graph is given to you in which for three different value of voltages, this value, this one, and this one, for all these three different values, you are getting the same current. You are getting the same current. So here VI relationship is not unique one. Obviously we can say Ohm's law is not obeyed. Okay, so here always remember this thing, Ohm's law is obeyed by particular substances in a certain fixed conditions, or we can say situations. Clear to all of you? Now, resistivity of various materials. So see, we know this thing, the materials available in the nature are classified in three categories as far as the resistivity, or we can say conductivity of the substances is concerned. Okay. Now, the materials available in the nature are classified as conductors, semiconductors, and insulators, depending on their resistivities. Conductors are such materials which have very low resistivity. The resistivity of such materials which are known as conductors, that is of the range of 10 raised to minus 8 ohm meter to 10 raised to minus 6 ohm meter. So we can say, in other words, for this type of materials which are classified as conductors, the conductivity that is large one, because conductivity that is reciprocal of resistivity. So that is large one. Now, insulators are such substances for which the resistivity that is tremendous large one, and that is of the order of 10 raised to 10 ohm meter to 10 raised to 12 ohm meter. It implies that we can say conductivity of these substances that is nearly equal to 0. Okay, there will be no conduction process in this type of substances, so are known as insulators. Okay, here we can say, in other words, the resistivity of insulators are almost 10 raised to 18 times than that of the conductors, and conductors are metals. Then third category, semiconductors. Semiconductors are such materials which have moderate resistivity. It implies that the resistivity of semiconductors that is greater than that of metals, or we can say good conductors. But the resistivity of semiconductors that is less than that of insulators. એટલે કે કંડક્ટર્સ અને ઇન્સ્યુલેટર્સ એની જે રેઝિસ્ટિવિટી છે એ બેની વચ્ચેની રેઝિસ્ટિવિટી સેમિકન્ડક્ટર્સની હોય છે. ક્લિયર ટુ ઓલ ઓફ યુ બેટા? Now next topic, that is resistors. Now resistors available in the market, or we can say the resistors which are commercially used are of two types: wire wound resistors and carbon resistors. These wire bound resistors are made by alloys like manganese, constantan, nichrome, or similar ones. These wire wound resistors are made by the winding of wires on non-conducting base. Okay, but nowadays when carbon resistors are developed, these wire wound resistors are outdated. Okay, here if we use wire wound resistors, then wire wound resistors are very bulky for large value of resistor, too much heavier one with large dimensions, and will be very much costly. And this material itself, alloys, are also costly material. Okay, no doubt they are insensitive for temperature, but practically when we think about the wire wound resistor to use commercially, then it is not viable. Okay. Now, at present, carbon resistors are widely used commercially. Okay. Why? Because are very small in size, have wide range, 1 ohm to 100 mega ohm. In that wide range, carbon resistors are available. Okay. And they are made with the help of proper mixture of pure graphite and resin, and then that particular mixture is molded in the form of a very small cylinder, and then at the ends of cylinder two leads, metallic leads, are attached, so easily we can connect it in any circuit. Clear to all of you? These carbon resistors are very cost effective, very cheap, right? Cost wise. Now, their size that is very small, right? So, here to calculate the value of carbon resistor, a color code that is used. Now, let's discuss it. Now, register color codes. Say here, on any register given to you, the color bands are always given to you to calculate its value. And compulsorily on any resistor, three bands will be there. Fourth one, that is optional one. Fourth one, that is optional one. And now using first three bands, one can decide the value of that resistor. And the fourth band, that is for tolerance. Okay. Now see, out of the first three bands, first two bands will give you a figure of two digit, a figure of two digit. And the third band, that will give you the multiplier of this figure in terms of power of 10. Now see here, this particular color code is internationally accepted. So worldwide, in any manufacturing unit, if any register is produced, then its value that will be decided with the help of this particular color code. Means this color code that will be followed by each and every register producer. Okay. Now see here, the color bands are black, brown, red, orange, yellow, green, blue, violet, gray, white, silver, gold. So first two color bands, that will be always from black to white, which will decide a figure of two digit, out of which the first color band will give you the 10th value of the figure, and second color band will give you the ones for that figure. Then third color band, that will give you the multiplier in terms of power of 10. Now see, if you remember this color code, then values associated it are very simple. See, black, brown, red, orange, yellow, green, blue, violet, gray, white. Then simple. Allot the values from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the multiplier in the power of 10. That is also like the same one. 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3, up to 10 raised to 9. And then for gold and silver, the multipliers are 10 raised to minus 1 and 10 raised to minus 2. Clear up to this one? Now see, to remember this color code, suppose we make one such sentence like this: BB Roy go Bombay via Gateway. Now see, black, brown, red, orange, yellow, green, blue, violet, gray, white. Easily you can remember this one. Clear? Now let's discuss how the value is decided. See, here the register given to you, for example, in which four color bands are there. First one, that is yellow, second one, that is violet, third one orange, and fourth one gold. Now how the value is decided? આપણે discuss કર્યું કે first two band will give a figure of two digit. Okay. તો હવે yellow, with yellow the digit associated, that is 4. So we can write here first 4. So 4, that is the 10th value for the figure of 2 digit. Then violet. So with violet, the associated value, that is 7. So that is once. It implies that now our 2 digit figure, that is 47. Then third band that give you the multiplier in terms of the power of 10. So with orange, the multiplier associated, that is 10 raised to 3. So multiply this one by 10 raised to 3. It implies that now we can say the value of this given resistor, that is 47 into 10 raised to 3 ohm, or we can say 47,000 ohm, or you can write this is equal to 47 kilo ohm. Clear to all of you? The fourth band, that is of tolerance. Now see here the fourth band, that is gold. So tolerance related to gold, that is plus or minus 5%. So here we can write plus or minus 5%. So if you use the resistor in the circuit, and if the variation of voltage and current is such that, so the ratio V to I give you the variation of 5% in this particular value, up to that this resistor can work properly. But if beyond this range the variation takes place, then there are chances for the damage of this resistor. This is the tolerance. Okay. And if the fourth color is not given to you, this one, then be careful here. See the tolerance. No color means 20% tolerance. For all other colors, the tolerances are given to you. So if fourth band is not there, it doesn't mean that simply you write this value. Then you have to write the value and then tolerance plus or minus 20%. જો આ લખવાનું રહી જાય ને તો માર્ક જાય આપણા. ક્લિયર? સમજ પડી હવે બેટા? Temperature dependence of resistivity. See, when we discussed about resistivity, at that time we discussed this thing as temperature increases, resistivity also increases. તમને યાદ હોય તો આપણે એવું ડિસ્કસ કર્યું હતું કે as temperature increases, the kinetic energy associated with the thermal motion of electrons also increases. એટલે ઇલેક્ટ્રોન્સની મોશન સ્પીડી થઈ જાય છે. And due to that, the time between two successive collisions decreases. And rho, that is resistivity, rho, that is m upon any square tau. So rho inversely proportional to tau. Tau, that is the time between two successive collisions. હવે એ જો ઘટે તો resistivity વધે. Okay, no doubt. આ તો આપણે ડિસ્કસ કર્યું કે as temperature increases, resistivity also increases. પણ હવે કેટલું ટેમ્પરેચર વધે તો એને કોરસ્પોન્ડિંગ કેટલી રેઝિસ્ટિવિટીમાં ચેન્જ આવે. તો એ કેલ્ક્યુલેશન કેરી આઉટ કરવું હોય તો આપણી પાસે રેઝિસ્ટિવિટી એન્ડ ટેમ્પરેચર એની રિલેશનશિપ હોવી જોઈએ, રાઈટ? So the dependence of resistivity on the temperature, that is given by this equation. This is the empirical formula. With the help of large number of experimental observations, this one is prepared. So equation that is resistivity at any temperature T, rho T, that is equal to resistivity at a temperature T0, where T0 that is some reference temperature, into 1 plus alpha into T minus T0, where alpha that is known as the temperature coefficient of resistivity, and that will be given to you because it is different for different materials, and in text a table for alpha for different materials that is given to you. Okay, so here one can calculate the resistivity at a particular temperature T using this equation. Now, the same type of equation we can write for resistance also. We know when resistivity increases, resistance that will also increase with temperature. Now, resistivity rho that is Ra by L. So we can write here R at any temperature T, area of cross section of the conductor upon length of the conductor. So at temperature T or T0, area and length that is constant one. Okay, so we can write R at temperature T into A upon L, that is equal to R at temperature T0 into A by L into bracket 1 plus alpha T minus T0. Okay, so A by L cancelled. So we can write resistance at any temperature T, that is equal to resistance at any reference temperature T0 into 1 plus alpha T minus T0. Clear to all of you? Now, for different materials, how the resistivity changes with temperature, that is given to you. Suppose we think about the metals. Here the example of copper that is given to you. So graph of resistivity versus temperature that is given to you. And here we can observe this thing. As temperature increases, then initially the resistivity increases very slowly up to 50 Kelvin. But after 50 Kelvin, with temperature, the increase in the resistivity that is considerable one. Okay. Now, here you can observe this thing. See, above 50, non-linearly the resistivity increases. Means as the higher temperature we take, resistivity increases rapidly. Clear to all of you? Then after, if we think about the alloys, then we can say this thing, the resistivity of alloys that is almost independent of temperature. See here, one example is given to you, the relationship of resistivity of nichrome as a function of temperature, that is given to you. See, resistivity that is in terms of micro ohm centimeter. Micro ohm. Micro stands for 10 is to minus 6. Okay. Now see here, at 0 Kelvin, the resistivity that is this much. Then here at 800, the resistivity that is almost up to this one. So roughly you can observe this thing when here the change in the temperature that is up to 800 Kelvin. Change in temperature that is 800 Kelvin, and corresponding to that the change here in resistivity. If we take this one nearly 1, then 1 micro ohm. So 10 raised to minus 6 ohm centimeter. This much small variation takes place. So we can say at room temperature, in laboratory when we perform the simple experiments, at that time we can consider the resistivity of alloys that is almost independent of temperature. Clear to all of you, beta? Then after for semiconductors, so the graph of the resistivity versus temperature for the semiconductors that represent this thing. For semiconductor, as the temperature increases, resistivity decreases. Or in other words, we can say for semiconductors, with increase in the temperature, its conductivity increases. And why this happens, that we will discuss in detail in chapter number 14. Clear?